In the heart of Boston's prestigious Longwood Medical Area, Perini Building Company built the Richard A. and Susan F. Smith Research Laboratories for the world-renowned Dana Farber Cancer Institute. The 460,000 square foot facility, 13 floors above grade and 7 below, houses new laboratories and support offices to advance Dana Farber's research, identifying the causes and cures of cancer. The measures of success associated with the construction of this facility included the outstanding teamwork and collaboration of Dana Farber, Shepley, Bulfinch, Richardson, and Abbott, the project architect, and Perini, beginning early in the design development phase. The two key construction challenges of the project were the building's unique vibration-dampening foundation and the logistics management required to work safely and productively on the site. The Smith Laboratories building was constructed on a congested 28,845 square foot site. On the south side of the project, the building abuts the Medical Area Total Energy Plant, MATEP, a co-generating power plant that supplies energy to many of the medical area facilities. Early in the design development phase, subsurface explorations determined that the vibrations transmitted through the predominantly clay soils by MATEP's massive diesel generators exceeded tolerances permitted by the biomedical research planned at the new facility.
You can imagine looking at something that's magnified 120 times and a little tap on the table becomes an explosion in the microscope field. Or if you picture that we're trying to take a gene and using micromanipulators, inject a substance inside the nucleus of a cell, we can't afford to have vibration moving everything around all the time.
Lacking precedents upon which to base a solution, the project team brought together an expert team of engineering resources to evaluate approaches to the vibration isolation issue. In addition, construction-related issues such as severely restricted site accessibility, prevention of soil movement beneath adjacent structures during excavation, and groundwater cutoff were addressed. The project team proposed a 90-foot deep tie-back reinforced slurry wall founded on bedrock, creating one of the deepest building foundations in Boston that would cost-effectively serve as a vibration isolation dam, a rigid excavation support system, and a groundwater cutoff during construction. Slurry walls are commonly used in the construction of cut-and-cover tunnels for roadways and mass transit projects. With slurry wall project experience in both building and civil projects in Boston, New York, and Washington, D.C., the company was well prepared to manage the effort at the Smith Labs. Operations associated with the work, slurry panel excavation, cage fabrication, and concrete, were confined to the site. Each panel, 3 feet wide, 15 feet long, and 90 feet deep, was excavated using a clamshell bucket. A recyclable slurry of bentonite clay and water mixed on site was pumped into the trench during excavation to prevent cave-ins. Reinforcing steel cages, fabricated on the infield of the site during trench excavation, contained box-outs to accommodate the installation of tiebacks. 7,300 cubic yards of concrete were required to complete the perimeter wall. Once the 130-foot by 200-foot perimeter slurry wall foundation was completed, over 70,000 cubic yards of fill was excavated from the site. The slurry wall foundation is supported by 419 permanent tiebacks set in rows every 10 vertical feet and acts as a cofferdam within which the building rises from bedrock to street level. Permanent tiebacks are highly unusual in building projects. Drilling, grouting, and stressing the tiebacks so that they were firmly anchored into the surrounding bedrock required an extraordinary amount of care and inspection during installation. Structural steel columns were set atop footings built upon the bedrock at the base of the excavation. Columns along the building's perimeter stand a few inches from the foundation wall. The 6 parking levels and mechanical space chiller plant located below grade are thus isolated from the surrounding slurry wall to prevent the transmission of vibration to the building structure and the research floors above. The limitations of the site, access and laydown area, impacted construction sequencing. The size of the site and its proximity to operating hospital facilities dictated many of the methods Perini chose to construct the project and to prepare the construction schedule. Perini erected steel for the lower levels up to street level before it placed its first concrete-on-metal deck at grade. This gave ironworkers a work platform upon which they could temporarily lay steel and from which the tower steel could be more efficiently and safely erected. As the steel proceeded upward, Perini completed levels below grade under the shelter of the first floor deck without impacting the above-ground work. To avoid swinging loads into adjacent buildings, Perini used a Kodiak tower crane with a luffing boom to set steel and load equipment. Mobile cranes were brought on site to facilitate the installation of mechanical electrical systems and laboratory equipment on the upper levels. A floor opening at street level was used to lower two 2,200-ton chillers to be operated by Maytep as a satellite plant to level P7, 80 feet below grade. The pink and gray stone curtain wall is a pressure equalized system that minimizes water and air infiltration as well as condensation. Common in Canada, where the cold weather is more severe, the benefits of this technology apply to the New England environment as well, especially in buildings with higher levels of relative humidity required for research. The simplicity of the lab layouts masks the complexity of the HVAC and mechanical electrical systems required to support the facility. Exhaust fume hoods used in the labs are vented through stacks supported by structural steel extending 30 feet above the roofline. The building is provided with a separate potable and non-potable water system, deionized water system, CO2 system, and acid waste system. The level of teamwork on the Smith Laboratories project was extraordinary. A decisive owner and responsive design team contributed significantly to the success of the project. Throughout the construction process, there was a strong sense on the part of the owner, architect, engineers, subcontractors, and trades that they weren't just building a building, but contributing to a much greater cause.